In mesh analyze, we assume a mesh current running through a loop. You can draw this current clockwise or counterclockwise. Now, I decided I draw this one in clockwise. And this is mesh current I1. And this loop is loop 1. Now remember, the mesh current doesn't mean the physical current. We'll find out the physical current a little bit later. And also, you can draw the current running in clockwise or counterclockwise direction. On the right hand side, I also draw a clockwise mesh current here. And I call this one I2. This is loop 2. Next, I'm going to apply KVL for each loop. So, KVL for the loop 1. Again, the current enters the voltage source from the negative side. So, this is negative 12 volt. The current passing through R1. And the voltage across R1 is V1. However, we don't know exactly V1, but we can apply Ohm's law and say V1 equal to R1 and I1, because this is I1 passing through R1. So I can say the voltage across R1 is 2K I1 plus R3. Now R3 will be a little bit more complicated. For the I1, the current is moving down, so this is I1. However, R3 is shared between the two loops. So if you look at the right hand side, I2 will go up. When we analyze I1 in loop 1, we have to make sure the overall current is down. So it means we can say there are two currents passing through R3. One is I1, one is I2. And I1 must be bigger or larger than I2. So we can say the voltage across R3 is equal to the resistance 1K ohm, and the current is I1 minus I2. So this is equal to 0. This is our equation 1. Equation 2, we look at the right hand side here. And again, it will start from the voltage source. The current or the imaginary current I2 enter the voltage source from the negative side. So this is equal to minus 6. Here, we are assuming or we are analyzing loop 2. So the direction of the loop 2 or the I2 must go up. And again, you have I1 is opposite to the I2. So the overall current passing through R3, we can say this is I2 minus I1 from the perspective of loop 2. So we are using or we are analyzing loop 2. We plus R3 is 1K, and this time is I2 minus I1 to make sure the overall current is along I2. For this part, it's easy. I2 passing through R2. So the overall voltage drop is 3K ohm times I2. We write it down here. 3K I2. This is our equation 2. Now I will simplify equation 1, and you will get 3k I1 minus 1k I2 equal to 12. I want to make the coefficient of I1 and I2 a little bit simple, so you can choose at this stage to divide both sides by 1000. So it will make the coefficient of I1 become 3 I1 minus I2. When 12 divided by 1000, it is 12 times 10 to the minus 3. And 10 to the minus 3, the prefix is m. So it becomes 12m. So this is our equation 3. I do the same thing for equation 2. And you will get minus 1k I1 plus 4k I2 equal to 6. Simplify it, divide both sides by k, so you will get minus I1 plus 4I2 equal to 6m. This is equation 4. Now we can use the standard method either by substitution, elimination, or even matrix method you use to determine I1 and I2. So I can use elimination method. So I will say 3 plus 3 times equation 4, so I can eliminate I1. And from here, you will get 11I2 equal to 30m. From here, I2 is equal to 2.727 milliamp. Now I substitute I2 back to, say, equation 4. So substitute I2 into equation 4. So you will get I1 equal to 4I2 minus 6m, and you will get I1 equal to 4.909 milliamp. Now, the next question I want to answer is, what is the physical current passing through R3? Now, if you look at R3 here, we assume on the left hand side the mesh current I1 going down, and on the right hand side the mesh current I2 going up. But if you look at I1 is 4.909, I2 is 2.727, so it means the overall current must going down. So the physical current passing through R3 must equal to I1 minus I2. It means 4.909 milliamp minus 2.727 milliamp. And if you plug this one into the calculator, you get 2.182 milliamp. And the overall direction is down. Next, we can calculate the voltage across R3 with Ohm's law. So V3, the voltage across R3, equal to R3 times the real, the physical current passing through. So this is I1 minus I2, or 2.182. So you're getting 1k ohm times 2.182 milliamp. So you will get 2.182 volt. This is the voltage across R3. So let's look at again how mesh analysis work. In mesh analysis, we assume a current, a consistent current I1 flowing in the loop and also I2, but R3 share by different loop. So eventually we have to answer the question, what's the real physical current passing through R3? And we can first look at I1 and I2 and then find out the real current passing through R3. So this is the idea of mesh analysis. This question is the same as the previous one, except the polarity of E2 is reversed. So we have positive here and negative here. Now we can draw the first loop. So this is the loop 1, and we imagine again the mesh current I1 flowing around the loop 1. Now loop 2, you have two choices. You can draw this one in clockwise or counterclockwise. And even though you imagine, you think, okay, the current from 6 volt voltage source should coming from the positive side. But remember, mesh current is a fictitious current, so you don't need to, at this stage, to exactly along the physical current. So we can still draw the mesh current in the clockwise direction. So I will do this one in the clockwise direction. And our solution will eventually give the true direction of the current. So this is loop 2. Next, we're going to apply KVL on loop 1 and loop 2. So KVL on loop 1, and again this is equal to minus 12 for this one, and positive. The voltage across R1 is 2K multiply I1 plus the same argument, the voltage across R3 using Ohm's law is equal to 1K, but R3 is shared by 2 loops. So we are analyzing loop 1, so we have to assume I1 is bigger than I2. Again, this is I1, this is I2. So when we analyze loop 1, we have to assume I1 bigger than I2. So this is I1 minus I2. And here we have equal to 0. This is equation 1. Equation 2, we do the same thing. The only difference this time is the I2 enter E2, the voltage source 6 volt from the positive side. So we can write this one as positive 6. When we analyze R3, the same argument, we have to maintain the current I2 or through this direction. So in this case, when we analyze loop 2, we have to assume I2 bigger than I1. So plus 1K I2 minus I1 plus 3K I2. So this is equation 2. Now I will simplify equation 1 using the standard procedure. So you see this is equal to 3K I1, and this is equal to minus 1K I2 equal to 12. Equation 3. However, I can do the same thing. I can divide both sides by 1000, and this becomes 3I1 minus I2 equal to 12 times 10 to the minus 3. It means 12m. This is equation 3. From equation 2, we have minus 1k I1, and we have positive 4k I2, but this time we have negative 6. Divide both sides by 1000. We have minus I1 plus 4I2 equal to minus 6m. So this is equation 4. Now again, we want to use elimination, substitution, or matrix method to solve I1 and I2. Equation 3 plus 3 times of equation 4. So if you focus on I1, this is how I can eliminate I1. And minus 1 plus 3 times 4 equal to minus 1 plus 12. It means 11. So the same, we have 11 I2 here. For the other side, we have 12m plus 3 times minus 6m. So we have 12m minus 18m. So we have minus 6m. So this becomes minus 6m. I2 will become 6 over 11, and you will get minus 0.545 milliem. Next, we want to substitute I2 into equation 4. So we arrange the equation. We'll get 4I2 plus 6m. So 4 times minus 0.545 plus this is milliem plus 6m. So you get 3.82 milliem. Okay, now let's look at the physical current passing through R3. When we assume both loops, the mesh current flowing clockwise. For the R3, I1 is down, but I2 in this assumption is up. However, the sign of I2, what we find is negative. So it means our assumption should be reversed. So I will draw the I2 should be, in this case, going down as well. So the physical current I passing through 3 should equal to I1 plus I2. Remember, I already reversed the I2. So this one will become 3.82 MA plus 0.545 MA. You got 4.365 milliamp. And again, the voltage V3 across R3 will be R3 I3, and you will get 4.365 volt. So you can see, even though we reverse the I2, eventually we'll find I2 is a negative value. So you may ask this question: if in the beginning we assume this, instead of clockwise, if we assume a anti-clockwise, this one here, what will happen? So if we already assume an anti-clockwise, I2 here is already down, so our equation will be slightly different. And in particular, the equation passing through R3. So I can write it down, and I will let you solve this equation, and to prove you will get the same answer. For loop 1, I will do the same thing. So this is loop 1, and equation 1 will become minus 12 plus 2k I1. But this time, I1 and I2, they are passing through R3 along the same direction. So I will say this plus 1k I1 plus I2 equal to 0. Equation 2 will become, because I2 enters 6 volts from the negative side, so it will become negative 6, and this time again I2, so this is V2. V2 is I2R2, of course, and this is plus 3k I2. For this one, same, they both I2 and I1, they're parallel and moving down, so we can say plus 1k I1 plus I2 equal to 0. So we have slightly different of I1 and I2, but you can simplify that and solve it, and you will get I1 3.82 milliamp, and I2 you will get a positive value of 0.545 milliamp. This question requires to use nodal analysis in this circuit. In nodal analysis, we first find node. For example, we look at this node, we call it A. Next, we apply KCL at this node. Let's analyze the current going in and going out the node. The source 10 volt will push the current I1 going in the loop, and the source E2 we assume also push the current going in the loop, and we assume the current going down this path I3. Now again, this is the assumption. If when we solve the equation, find the loop current or any sign is negative, our assumption will be reversed. Next, let's write down the KCL at node A. So KCL at A should equal to I1 plus I2 equal to I3. Now that the idea of nodal analysis is to apply Ohm's law to the current. It means Ohm's law say V equal to IR. So I is equal to V over R. So what we really want to find is the voltage instead of current. So I1 plus I2 equal to I3 is just the starting point. So next we have to apply Ohm's law to I1, I2 and I3. Now this is important. Now we have to analyze the voltage. If we look at I1, we first assume the voltage at A is VA. So this is VA. Now on the other side of R1, this should be 10 volt. So the potential difference across R1 is 10 minus VA. And the current I1 should equal to the potential difference across R1 divided by the R1. So we apply Ohm's law, and it become I1 will become the potential difference 10 minus VA over R1, which is 2K, plus I2. This side of the resistor R2 is 5 volt, and the current we assume flow from the 5 volt to VA. So the potential difference is 5 minus VA across R2. So we can say V2 is 5R minus VA, and the current I2 should equal to the potential difference 5 minus VA divided by 8K. Now let's look at the current I3. The I3 passing through R3, and the potential difference across R3 is VA, and this is the ground. So this become VA divided by R3, which is 4K. The next part is find the common denominator and solve the equation and find VA. So we can multiply both sides by 8K. So this becomes 4, 10 minus VA plus 5 minus VA, and this becomes 2VA. And after expand and rearrange, you should get 7VA equal to 45. So VA equal to 45 divided by 7 volt, or equal to 6.429 volt. And we can check or verify everything. So if now VA is 6.429, so this is 6.429. So I1 will equal to 10 minus 6.429. Beg your pardon. This is 29 divided by 2K. So you will get 1.786 milliamp. I2 equal to, now this is interesting, the voltage at VA is 6.429, so it's actually higher than 5 volt the other side. So I2 should be reverse. So let's reverse it ourselves. So I2 should be draw this direction. Okay, after we find the potential. So this becomes 6.429 minus 5 divided by 8K, and we have 0.179 milliamp. And I3, this is 6.429 divided by 4K. You have 1.607 milliamp. Now let's check. After the correction, we should say I1 equal to I2 plus I3. So this is I1, and we add this together, we'll get exactly 1.786 milliamp. So I1 is equal to I2 plus I3. So they are consistent. First, look at how the current flow within this circuit. We have a current source 2 milliamp I1. So this is node A. We can assume that 2 milliamp here is injected into the node. Now I2 is flowing down, so at this node, this is I2. So we can say this is I2 equal to 1 milliamp. And this is I1 equal to 2 milliamp. So it is clear now the current at A will flow into R3 from A to B. So this is very clear now. We can assume VA, the potential at node A, is bigger than VB. Therefore, the current will flow through here, passing through R3 from A to B. The current passing down R1, so this is another current, and this is another current passing down R2. So we assume this is ground, it means 0 volt. Now we apply KCL at A and apply KCL at B separately. So KCL at A. Let's look at the free current. The current in must equal to the current out. The current in is 2 milliamp. So we can say this is 2 milliamp. 2M, the in, equal to out. The first one is the one passing through R1. Now the potential difference here is VA minus 0, because this is 0 volt. So we can just write the I passing through R1 as VA over R1. So we can put it a bit quicker. So the current which is going out from A, one of the current, is VA over 2K. The other current is the one passing through from A to B. And now the potential difference is VA minus VB. So the current passing through is VA minus VB divided by R3. So this is out from the perspective of node A. So this is this side, VA minus VB over 3K. Next, let's look at KCL at B. So there are 1 in, 2 out. So the 1 in is this one. So this is the current flowing into node B. And we have VA minus VB divided by 3K, the current flowing into node B, equal to the current flowing out. The first current flowing out is this current. And this current flowing out must equal to the voltage VB divided by R2. So this is VB divided by R2 is 4K plus another current. This is the one given. This is another current source, which is 1 milliamp. So this is 1 amp. Equation 1. Equation 2. So the next things, of course, is simplify the equation. The basic idea is ask yourself what you really want to find. You want to solve VA and VB from equation 1 and 2. So we try to simplify the coefficient. The best way this time is we multiply the common denominator. So I will say from 1, I will do it is multiply 6K. So 6K multiply 1. I rearrange the equation, make it a bit nice. So it becomes 3VA plus 2VA minus VB equal to 12. This is equation 3. For equation 2, I will do 12K times equation 2. And I will get 4 bracket VA minus VB equal to 3VB plus 12. And I will get 4. So I will further simplify 3 and 4. Number 3, you will get 5VA minus 2VB, and this is equal to 12. This is 5. From 4, I further simplify, and this is equal to 4VA minus 7VB, and equal to 12. This is 6. Now I can eliminate VA or VB, so I decided to eliminate VA first. It doesn't matter what method you use as long as you can solve VA and VB. So I will say 4 times 5 minus 5 times 6. From here, I can eliminate VA. And what I get 27 VB equal to 12. So VB equal to, beg your pardon, is negative 12. Yep. So it's negative 12 over 27 volt and equal to minus 0.444 volt. I substitute VB and find the VA. So you will find VA is equal to, say, I substitute into number 5. So substitute VB into 5. And from here, I will say this VA is equal to 1/5 of 2VB plus 12. Substitute the number and you will get this one equal to 2.222 volt. Okay, let's check and in particular find the current passing through R3. So VA is 2.22. So let's put down value here, 2.22 volt. VB is negative 0.444 volt. So our assumption VA bigger than VB is correct. However, VB is actually negative volt. So the I3, the current passing through R3, it means this one, I call it I3, is equal to 2.222 minus 0.444 divided by 3K. If you plug this number, you will get this equal to 0.889 milliamp. You can also check the current passing through R1. So I have to put a bit clear here, R1. This is the current passing through R1. And of course, it's VA divided by R1. So this is 2.222 divided by 2K. So this is 1.111 milliamp. The current passing through R2 is equal to, this is 0. So the current should be reverse. Yep. So will mean this should be the direction of the current passing through R2. Okay, let's key up here. Yep. So this is I3 going in, and it makes sense because this current source going to here will go through here, and this one go through here. But this is ground, so therefore in order the current passing up the R2, the potential at here should be negative. So just check the current passing through R2, 0 minus negative 0.444 divided by 4K. So it should equal to 0.111 milliamp. And you can see when you add these two, this equal to 2 MA. So this is correct. And also when we add I3 and I passing through R2, you also get 1 amp. So when you add this together, you will get this one 1 milliamp. So they're all consistent. In this question, we are going to find the Thevenin equivalent circuit. It means we focus on the RL, the load resistor, and we'll replace the rest of the circuit by a potential divider. It means a voltage we call Thevenin voltage, a resistance we call Thevenin resistance, and this is our RL, the load resistor. To find the Thevenin resistor, we first remove the load resistor and then remove any sources inside the circuit. Now we want to find the equivalent resistance of these resistors. R1, R2, they are connected in parallel, and R3 is in series of R1 and R2. So the Thevenin resistance is R3 plus R1 parallel R2. And the answer is 5K ohm. Next, we're going to find the Thevenin voltage. Again, we remove the load resistor. And the voltage across these two ends is the Thevenin voltage. The resistor 2.6 kilo ohm is connected to here, and the voltage at this point is the same as the voltage at this point. It means the voltage across AB is the same voltage CB, because there's no current through the 2.6 kilo ohm resistor. So we can find the Thevenin voltage by applying the potential divider again. So the Thevenin voltage is 6 volt. So this is 6 volt. And the Thevenin resistance is 5K ohm. Now we can calculate the current passing through the load resistor. So this current I passing through the load is equal to V, the Thevenin voltage, 6 volt, over the overall resistance is the 5K plus the load resistance, which is 1K. So this is equal to 1 milliamp. The voltage across the load resistor VL we can either use Ohm's law or we can use potential divider formula. So this is 6 volt. Remember, this is a 6 volt of the Thevenin voltage now. And this is 5K plus 1K, 1K. And this is equal to 1 volt. In this question, we want to find the Thevenin equivalent circuit for RL. First, we want to find the Thevenin resistance. Now, I'm going to remove the source. In this case, we have a current source. The rule for removing the current source is just leave the current source open. So I'm going to withdraw the circuit like this. Now you can see one of the end of R1 is not connecting to anything. So we can technically remove R1. And I'm going to withdraw the circuit and make it clear again. Now you can see the Thevenin resistance is equal to 150 ohm plus 200 ohms. And it is equal to 350 ohms. Next, we're going to find the Thevenin equivalent voltage. Now I have removed the load resistor. And the voltage across AB is the same voltage as AC. So this is C and this is A. Now we have a current source. So this current will flow through this loop. And the current here is 50 milliamp passing through the 150 ohm. So the voltage across AC, it is the Thevenin voltage, is equal to 50 milliamp times 150 ohms. And you will find this equal to 7.5 volt. So what it means is the whole circuit can be replaced by a Thevenin voltage, which is 7.5 volt, and connected in series of a Thevenin resistor. This is equal to 350 ohm. And this is our load resistor. And this is equal to 50 ohm. Now we can calculate the voltage across RL. And this is again a potential divider. So VL is proportional to 7.5 volt. And the denominator of the proportional constant is 350 plus 50. The numerator is 50. So the voltage across the load resistance is 0.9375 volt. And the current across the load resistor can be calculated using the Ohm's law, 7.5 volt over 350 ohm plus 50 ohm. And you will find this is equal to 18.75 milliamp. In this question, we are going to find the Norton equivalent circuit on RL, the load resistor. Norton equivalent circuit is different from the Thevenin equivalent circuit. In the Norton equivalent circuit, instead of the voltage, we use a current source. So this is the current source, and we call this Norton current source. And similar to Thevenin equivalent circuit, we need to find the Norton equivalent resistance. So this is Rn, and we connect these two in parallel. From here we can connect our load resistor. So how to find the current source and the Norton resistance? Let's do it using this example. To find the Norton equivalent resistance, we first remove the RL, and then we replace any source using the usual rule. It means we replace the current source by open circuit, and we replace any voltage source by the short circuit. So I'm going to withdraw this circuit here. So the Norton equivalent resistance Rn is equal to 2k ohm plus 3k ohm and equal to 5k ohm. And this is exactly the same as the Thevenin resistance. Next, we are going to find the Norton equivalent current source. First, we are going to replace the load resistor RL, but this time, instead of leave it open, we'll connect RL by short circuit. So the RL now is replaced by short circuit, and our aim is to find the current passing through this part, and this is our Norton equivalent current. So we can apply the rule for current divider. So IN, the current we want to find, is proportional to 20 milliamp. The denominator of the proportional constant is the sum of R1 and R2. It means 2k plus 3k. We want to find the current passing through R2. It means along this branch, and in the numerator it is the R1 control how much current passing through here. So this is R1 equal to 2k, and you should be able to find this is equal to 8 milliamp. Now I replace this circuit by this one, and the IN is 8 milliamp, and the Norton equivalent resistance is the same as the Thevenin equivalent resistance and is equal to, in this case, 5k ohm. Our RL, the load resistor, is 3k ohm. Now we can calculate what is the current passing through the RL, it means the IL. And again, you can see here, this is a current divider circuit. So IL is proportional to 8 milliamp. The proportional constant, there are two parts. The denominator equal to 5k plus 3k, and the numerator is 5k, and you will find this is equal to 5 milliamp. And the voltage across the load resistor, this time VL, is equal to IL and RL, and you should be able to find this is 5M multiply 3k, and it's equal to 15 volt. First, we are going to remove the load resistor, and then we replace the source. Now we have a current source, so we can just leave the current source open. So the Norton resistance is the resistance across AB, and it is equal to 2k plus 3k, and equal to 5k ohm. Next, we have to find the Norton equivalent current source. Now we are going to replace the RL, the load resistor, by short circuit. So the Norton equivalent current is the current passing through this part. And you can see we can apply the formula for the current divider to find the IN. And it's proportional to the 20 milliamp. And the denominator of the proportional constant is the sum of R1 and R2. The numerator is the resistance of R1. So you will find this is equal to 8 milliamp. So we can replace our original circuit here by the Norton equivalent circuit. This is the Norton equivalent current source. And this is connected in parallel with the Norton equivalent resistor. And now we connect our load resistor in parallel. To find the current passing through the load resistor, we say this is IL, and again this is proportional to the IN, in this case 8 milliamp. So 8 milliamp. The denominator of the proportional constant is the sum of Rn and Rl. It means it is equal to 5k plus 3k. And the numerator is equal to Rn, which is 5k. And the result is 5 milliamp. And the voltage across the load resistor we can find from IL multiply RL. It means 5 milliamp times 3k ohm, and it is equal to 15 volt. To find the Norton equivalent circuit, we first find the Norton equivalent resistance. Let's first remove the load resistance and replace the current source by an open circuit. Again, the 100 ohm resistor is opened, so we don't need to worry about this one. And the Norton equivalent resistance is the 150 ohm and 200 ohm connected in series. Rn is equal to 150 ohm plus 200 ohm, and it is equal to 350 ohms. Next, we want to find the Norton equivalent current source. Now we have to replace the load resistor by a short circuit. The Norton equivalent current is the current passing through the short circuit part here. So this is IN, and this is what we want to find. Again, we can see this is 50 milliamp, and it's split into two paths. And we want to find the current passing through the 200 ohm resistor. Now, IN, therefore, proportional to 50 milliamp. And the denominator of the proportional constant is 150 ohm plus 200 ohm. And the numerator is the 150 ohm of the opposite branch. And you will find this is equal to 21.429 milliamp. So our original circuit here is replaced by the Norton equivalent current source and the Norton equivalent resistor connected in parallel. This is IN and this is RN. And now we can connect our RL in parallel. IN is equal to 21.429 milliamp. Rn is equal to 350 ohm. And RL is equal to 50 ohms. Now we can calculate the current passing through RL. So IL again is proportional to 21.429 milliamp. The denominator of the proportional constant is the sum of Rn and RL. It means 350 ohm plus 50 ohm. The numerator is 350 ohm. And the result is 18.75 milliamp. The voltage across the load resistor is IL times RL. It means 18.75 M times 50 ohm. And it is equal to 0.9375 volt.